Offshore winds are strong and steady, making them an ideal, reliable source for clean energy. But most offshore wind turbines are fixed to the seabed, limiting them to shallow coastal waters. The problem is, the best wind resources, about 80%, are in waters too deep for traditional turbines. Building fixed towers in the deep ocean is costly and impractical, leaving this vast energy source untapped. This is where floating wind turbines come in. Mounted on anchored platforms, they unlock these deep water resources. This innovation is crucial for expanding renewable energy and meeting our global climate goals. These are not just wind turbines. They are colossal power plants, some taller than skyscrapers, operating in the planet's most challenging environments. So, how do you anchor a structure of this magnitude, not to the seabed, but to the very water it sits in? How do you ensure it remains upright and operational amidst relentless waves and powerful winds? The answer lies in a masterful application of fundamental physics, a delicate dance between weight and water that begins with a principle discovered over 2,000 years ago. The core principle is buoyancy, first articulated by the ancient Greek mathematician Archimedes. It's the same force that allows a colossal steel ship to float. To harness this force, engineers design enormous hollow substructures. These platforms, whether they are deep draft cylinders known as spar buoys or sprawling multi-legged semi-submersibles, are engineered to displace a massive volume of water. The weight of the water they push aside creates an upward buoyant force. This push is meticulously calculated to precisely counteract the immense downward pull of gravity on the entire structure from the submerged platform to the tip of the highest blade. This perfect equilibrium is what allows the multi-thousand-ton turbine to float. But simply floating isn't enough. A power plant is useless if it capsizes in the first storm. This is where the science of stability becomes paramount. The structure must be a steadfast foundation, capable of withstanding the constant dynamic forces of the open ocean, the push of the wind, the ceaseless motion of waves, and the pull of currents. It must not just float, it must endure. Achieving this resilience requires a clever manipulation of two key points: the center of gravity and the center of buoyancy. First, engineers lower the structure's center of gravity by placing heavy ballast, like concrete or water, deep within the submerged portion of the platform. This low center of gravity acts like a weighted keel on a sailboat, constantly pulling the structure towards an upright position. In contrast, the center of buoyancy, the geometric center of the displaced water volume, is designed to be positioned relatively high. The vertical separation between these 2 points is the secret to the platform's inherent stability. When a wave tilts the platform, the shape of its submerged section changes, causing the center of buoyancy to shift. Now, the upward buoyant force and the downward force of gravity are no longer aligned. They create a powerful rotational effect known as a righting moment. This moment acts like an invisible hand, powerfully pushing the platform back to its vertical, stable position. This self-correcting design is what allows these giants to ride out storms and operate reliably in the roughest seas. It is this elegant interplay of buoyancy, gravity, and fluid dynamics that makes floating wind power possible, a testament to human ingenuity, transforming scientific principles into resilient structures that unlock the vast energy of our deep oceans. Floating wind technology isn't a one-size-fits-all solution. The immense challenge of keeping a towering 250-meter-tall wind turbine stable in the open ocean has led engineers to develop several ingenious designs. While many variations exist, they generally fall into 3 principal categories, each with a unique philosophy for achieving stability. Let's explore the most common: the spar buoy, the semi-submersible, and the tension leg platform, or TLP. First, the spar buoy. This design achieves stability through sheer physics, much like a fishing bobber. It features a single, long and slender cylindrical hull that extends deep below the surface, sometimes over 100 meters. This hull is filled with heavy ballast, like concrete or iron ore, at its base. This creates an extremely low center of gravity, far below the platform's center of buoyancy. When waves or wind push the turbine, this powerful righting moment pulls it back upright. The world's first commercial floating wind farm, Hywind Scotland, successfully uses this design. However, their massive draft makes them difficult to build and deploy, requiring very deep ports and complex offshore installation. Next is the Semi-Submersible, currently the most popular design for new projects. Instead of a deep keel, it uses a wide, stable base. It consists of 3 to 5 buoyant columns connected by a submerged pontoon structure. This design, similar to a catamaran, creates a large waterplane area, which provides excellent stability by resisting pitching and rolling motions from waves. Its major advantage is its shallow draft. This allows the entire structure, turbine and all, to be fully assembled in a standard port and simply towed out to sea. This dramatically simplifies logistics and reduces costly, weather-dependent offshore construction, as seen in projects like Windfloat Atlantic off the coast of Portugal. Finally, we have the tension leg platform, or TLP. This design takes a completely different approach, relying on mooring for its stability. The platform itself is highly buoyant, constantly trying to float higher, but it's held firmly in place by taut steel cables, or tendons, anchored directly to the seabed. This constant tension virtually eliminates all vertical movement, making it the most stable of the 3 designs, almost as rigid as a fixed bottom foundation. This exceptional stability reduces stress on the turbine. However, the precision engineering and complex installation of the tendon and anchor system make it a more costly and site-specific solution. The choice between these platforms is a complex balancing act. Engineers must weigh the superior stability of a TLP against the deployment flexibility of a semi-submersible, or the deep water performance of a Spar against its logistical challenges. This ongoing innovation is creating a versatile toolkit of technologies, unlocking vast new areas of the ocean for clean energy generation and pushing the boundaries of what's possible in our sustainable future. The Spar buoy is a marvel of simplicity, a long vertical cylinder with heavy ballast at the bottom. Most of its length is submerged, making it stable and less affected by surface waves. If tilted, gravity quickly rights the platform. If tilted, buoyancy quickly rights the platform. Hywind Scotland, the world's first commercial floating wind farm, uses this design. Spars are ideal for deep water. They require deep ports for assembly. They require deep ports for towing. Their straightforward design means fewer moving parts. Their straightforward design means lower long-term costs. Despite logistical challenges, Spar buoys are proven leaders in floating wind. The semi-submersible platform uses a wide, shallow draft base with multiple buoyant columns. Its stability comes from spreading its columns far apart, resisting tilting from waves. Windfloat Atlantic in Portugal showcases this design, supporting some of the world's largest turbines. Semi-submersibles can be fully assembled in standard ports and towed to sea, simplifying logistics. They're structurally complex but offer flexibility and ease of deployment. Their large surface area can face strong wave forces, but their practicality makes them popular. Semi-submersibles are a go-to choice for many floating wind projects. The tension leg platform, TLP, achieves stability through tension. A buoyant platform is anchored by tight steel tendons, holding it firmly in place and minimizing movement. This design nearly eliminates vertical and horizontal motion, making TLPs the most stable floating platforms. Provence Grand Large in France is pioneering TLPs for wind. TLPs use less material and reduce turbine wear, but installation is complex and requires precise anchoring. Their stability and potential cost savings make TLPs an exciting future option. TLPs could redefine floating wind in challenging environments. The journey of a floating wind turbine from concept to reality is a monumental feat of engineering. It all begins on land with a critical decision: The choice of platform material. This foundation sets the stage for the entire project's construction, deployment, and operational life. Steel is a traditional choice, leveraging decades of shipbuilding experience. Its high strength-to-weight ratio is a key advantage, but it requires specialized coatings and maintenance to combat saltwater corrosion. Concrete, on the other hand, offers a compelling alternative. It is inherently resistant to corrosion, potentially leading to a longer lifespan with lower maintenance costs. The materials can often be locally sourced, reducing the project's cost and carbon footprint. Regardless of the material, these platforms are built using a modular approach. Massive sections are fabricated and then brought together for final assembly. Once the platform's base is complete, the towering mast is hoisted into place, followed by the nacelle, and finally, the enormous blades are meticulously attached. This entire assembly process typically happens quayside, at the port. Performing these complex lifts on solid ground provides a controlled environment, shielded from unpredictable weather. This enhances safety and allows for the use of large land-based cranes, making the operation more efficient and faster than working offshore. The platform design itself varies. Semi-submersibles are stabilized by buoyancy and are a popular versatile choice. Tension leg platforms, or TLPs, are held by taut vertical tethers, offering excellent stability in specific water depths. Spar buoys are long, weighted cylinders that float vertically. Their immense draft provides incredible stability, but requires very deep ports for assembly and specialized towing. Once assembled, a fleet of powerful tugboats tows the towering structure out to sea. At the site, the critical installation begins. Mooring lines or tendons are connected to seabed anchors. Finally, a specialized vessel connects the subsea power cable, creating the vital link to the onshore grid. After a comprehensive series of commissioning tests, the turbine is ready. The brakes are released, the blades catch the wind, and it begins its mission, harvesting the power of the ocean winds to deliver clean, renewable energy. Floating turbines stay in place thanks to mooring systems' networks of lines anchored to the seabed. Catenary moorings use heavy chains that curve along the seabed. Taut moorings use stretched synthetic lines. TLPs use vertical steel tendons under constant tension for ultimate stability. Anchors vary by seabed drag embedment, suction, gravity, or drilled piles. Power from the turbine travels to shore via a dynamic cable, designed to flex with the platform's movement. These cables use special shapes and buoys to handle waves and tides. Secure mooring and flexible cabling are vital for reliable offshore wind. Together, they keep turbines steady and connected to the grid. The ocean is harsh saltwater corrodes steel, and storms test every structure. Engineers protect platforms with marine coatings, sacrificial anodes for cathodic protection, electrical cathodic protection systems, impressed current. Maintenance is challenging. Technicians need specialized service vessels. Major repairs may require towing turbines back to port. Sensors monitor turbine health. They send real-time data to operators on shore. Automated systems can adjust turbine controls or shut down turbines during storms. Designs are tested in wave tanks and simulations, and for hurricane-force winds at sea, High Wind Scotland shows floating wind can survive the toughest conditions. Durability and smart monitoring are key to offshore wind success. Floating wind technology is unlocking vast new areas for clean energy, especially in deep waters. Strong, consistent offshore winds mean more reliable power for the grid. Countries with deep coastlines like Japan, Norway, the US can now harness their wind resources. Every floating turbine reduces fossil fuel use and cuts emissions. Costs are falling as technology matures, making floating wind more competitive. Floating wind is a bold step toward a sustainable, renewable future. By harnessing ocean winds, we're building a cleaner world for generations to come.